Okay, in this video I want to talk about another definition of a derivative, which is often called the definition of the derivative at a point, and it's also called an alternate definition of a derivative. But it's very useful, and it's based on the same type of reasoning that we used in the previous definition. So let's set it up. Well, in this case, we want to find the derivative at a particular point, and we're going to use this point on the left. And we're going to call that x value c, just a constant. So we're going to use this particular formula when we know an x value that we want to find a derivative at, and we know a function definition. So the function is f of x, the x value is c, and the value of the function at that point is f of c. And we're looking to find the slope of the tangent line, or to find the derivative at that point. So as in the previous example, we have a line that's drawn tangent to the curve at x equals c, and we're trying to find the slope of that line. Well, we're going to go about this kind of in the same way that we went about in the last one. We're going to start with another point, and we're going to make a secant line connecting those 2 points, like so. Now the second point over on the right, we're just going to call it x. Rather, the x value is just x. It's some variable value of x, as opposed to the c on the left, which is some constant value of x. So therefore, the coordinates of that second point are x, comma, f of x. And so we can find the slope of that secant line, which again means the average rate of change of the function over the interval from c to x. And so that slope of that secant line is, in terms of slope, y2 minus y1. In this case, it would be f of x minus f of c, my 2 y values, the difference of my 2 y values, or my change in y. And we're going to divide that by the change in x, which is the distance from c to x, or x minus c. So we divide that change in y by the change in x, and we have a formula for the average rate of change that is very similar to the expression we had in the last video. And again, that is the slope of the secant line. Well, in order to find the slope of the tangent line, again we have the same problem that we only have 1 point instead of 2 points. We're going to need to move that second point further and further to the left. So what we're going to do then is have x, the variable quantity for x, getting closer and closer to c. And so you can see the x value moving along the line, or the point moving along the line as the x value gets closer and closer to the original value c. And each stage along the way, we could draw a new secant line and calculate the slope of that line. And we would see that both the secant line is getting closer and closer to approximating the tangent line, and the slope of the secant line is getting closer and closer in approximation of the slope of the tangent line. Then eventually, as that point and as the x value gets closer and closer to the original value c as to be indistinguishable from c, then we're going to have 2 points that are infinitesimally close to each other, and we can still find the ratio of the change in y to the change in x. And that will give us the slope of the tangent line. But once again, we're going to use the limit concept here. We want the x value to get closer and closer, move to the left until it's infinitesimally close to c, and just about, or infinitesimally close to c is good enough. And that gives us the instantaneous rate of change, or the rate of change at that particular point. And that is the slope of the tangent line. Now in the coming videos we'll see how this is used, but it's a slightly different formula, and yet again it's similar to the one we've done in the past videos.